So welcome to all of you to the second lecture of the SEEKS WICT. So in the first lecture we defined the notion of nice tree decomposition, and we did our first dynamic programming algorithm on such a graph, right, for maximum weight independent set, right. Now dependent set. Okay. In this lecture we will see 2-3 more examples of how to do dynamic programming algorithm on graphs of bounded tree width, and yeah, so just to get a hang of this new notion. So the next problem that I have selected is a 3 coloring problem. Okay. So what is a 3 coloring problem? So before we even get here, let's try to understand what are we trying to understand. Okay. So we want to solve 3 coloring problem, right. So what are we looking for, okay, in 3 coloring? So you are given a graph G, you are looking for a function f from vertex set of Z to 0, 1, 2, such that for every edge uv in E of G, what is the property? F of u is not equal to f of v, right. So I want to test whether graph is 3 colorable or not on graphs of bounded tree width. So try to see what kind of divide and conquer algorithm we could have gotten. So suppose we had a separator S and these are the partition of my connected components into 2 pieces A and B. Then we ask ourselves, what are the possible partial solutions of S could be? So we know that any partial solutions of S could be a potential 3 coloring of S. So the way we go about is that we enumerate all 3 colorings of S, right. So you enumerate basically all function from S to 1, 0, 1, 2, okay, or maybe doesn't matter. Let's just put it. Let's see what are we using, 1, 2, 3 in the later. So let's just say 1, 2, 3. Okay. So let me change here also that not 0, 1, 2, but rather 1, 2, and 3. Okay. So we enumerate. So now here it is. Okay. Now you are enumerating such functions like f1, f2, fl, where L is upper bounded by 3 to the power mod s. Now what are we doing after this? Once we have decided coloring here, right, what are we looking for? So we are looking to find a coloring. We are looking for in this, what are we looking here? We want to find a coloring of, okay, 2 classes of graph, basically graph induced on say A union S and graph induced on B union S, and a graph G has a 3 coloring if and only if graph induced on A union S and graph induced on B union S has a 3 coloring, that so it will take F1 and take F, right. So you are basically looking, can we extend the 3 coloring of graph induced on S given by F1 to a 3 coloring of A, and similarly for B. Okay. Now, so basically this is kind of a partial extension of this 3 coloring, and if F1 can be extended to a 3 coloring of this graph, and if F1 could be extended to 3 coloring of the other part, then we know that there is a 3 coloring of the whole graph, right. So basically if you do recurrences, then this will lead to T of n is like some 3 power k plus 1 if the size of S is k, and at most 2 times T1 by 3, and so this will be again give you some n to the power big O of k time algorithm. Okay. But this tells us that what are we looking for as a partial solution at any point of time? That is basically partial 3 coloring of my graph. Okay. So with that in our mind, Okay, so we'll see how to do this. Okay, so for Bx is a vertices appearing in node x as before, and capital Vx denotes the vertices appearing in the subtree rooted at x, and for every node x and coloring of Bx to 1, 2, 3, we compute the following Boolean variable, which is true if and only if C can be extended to proper 3 coloring of graph induced on V of x. So we start with the 3 coloring. Okay, so this is here is a is a node here, and C is a partial 3 coloring, and we are asking, what are we filling is this is 1 if there exists an extension of 3 coloring, meaning you can come up with another color which is identical at f, but and so this is the next color, and that coloring has a property that for any edge, if you look at the endpoints of the color colors of the endpoint, then they are distinct. Okay, so now the question is, now you are given the values for the children, how will you determine the EXC for a particular bag or particular node? Okay, and that is very easy, because if there is no children, you are leaf, then what are you going to do? You are going to do very simple, is that you look at a particular coloring. If it is 0, so the particular coloring is going to assign either 1, 2 or 3, and that's trivial. Now look at any introduced node. So what is introduced node? So what is, notice, as always I have told you, introduced node means that there is a bag UW, okay, and a vertex V is introduced. So you are getting a new graph with edges of V being either restricted to either between V and W. So this is how the world looks like this is, okay. Now, okay, so now I have assigned V, okay. So given a child Y, which is this child Y, sorry, child Y, okay, and so what is this? We say, look, fine, whatever may be the partial 3 coloring of this B, well, it has to be a 3 coloring, so you start with a partial 3 coloring, so it's so if I forget the color of V, then that provides a partial 3 coloring of the bag Y. So now I ask myself, okay, if I assign this color, I know, and where are its neighbors, where are the edges? Its edges are either to U or to W or to none. So if I ask, is this coloring extendable? So this coloring is extendable if and only if, right, CB is not equal to CU for every neighbor U of V, right. So if I look at, right, so basically I look at so I have a coloring C given, okay, I look at the coloring C prime, which is restricted to here, the vertices contained in this bag, in particular UW, and I say, hey, is that associates to 1, okay, then I put it 1, okay. Now what about forget child? So forget child means you are forgetting a vertex V. So I am going to assign a coloring. I say, hey, look at all the possible extension of this coloring, meaning if I have a coloring C given to me, okay, then I say, look, E of XC is true, right, is 1 if and only if, what is 1? E y comma C prime is true for one of the 3 extension of C to be Y, because I know that, okay, if it is a 3 coloring, valid 3 coloring, then the child which I am forgetting also gets some color either 1, 2 and 3, and what is C prime? C prime is the extension, you fix C, and for the vertices which you are forgetting, say view, you assign, oh, is there a coloring where the V gets 1? If that is answer is 1, then I put, oh, no problem, if this, what happens if gets V gets 2, is that evaluate to 1, so on and so forth, okay. And now what about join node? Join node is, what does the join node mean? Basically join node is like this. So I have a 3 coloring extension to the whole graph. If I look at this and I look at this graph induced on this and this graph induced on this, which is basically I look at my child node with the same coloring C, right, Y1C, I said, does that evaluate to true? Well, yes, if that evaluates true, that already is stored here. Is the other child with the same C evaluates true? If it evaluates to true, then I know that I evaluate, meaning I have a 3 coloring for the whole graph. So 3 coloring of whole graph if and only if 3 coloring of the left side given here, 3 coloring of the right side given here stored. So if both of them are 1, then I know there is a 3 coloring for the join node, and that's it, right? And we can actually formally prove some of these things. So let's just try. Okay. So let's try to show this. Okay. Okay. So it will help us, right? So basically, what is this? This is a join node. Okay. Okay. So now okay. How do I show? Look. Okay. Now notice what is the meaning that this evaluates to 1, this evaluates to 1. What is the meaning of this? Meaning of this is what is the part, what does there exist a coloring of graph below this, right, with coloring C. So some coloring has been assigned to these guys. Okay. I ask myself, so now what can, if EY1 of C evaluates to 1, it means there exists some coloring of the graph induced on this. Okay. So let's call that coloring F1. Let's look at the, and what is this evaluates to? It means there is a function F2 which evaluates to true. Okay. 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 So now I will show that if, like, this is AND, right? So if both of them evaluates to 1, then this definitely evaluates to 1, and if this evaluates to 1, then we know there exists a coloring which evaluates to both of these will evaluate. So suppose if this evaluates to 1, means there is a coloring F1 which has this property, there is a coloring F2 which has a property which extends. Now I will say just take a new F which is basically F1 O F2. Okay, this is basically concatenation. So what is the, right? So let's say concatenation. So okay, basically what is that? If for any vertex y which is not here, you follow F1 for y. Let's say okay. So suppose I had a vertex A here and some vertex V here in this side of the graph. So what is f of A is nothing but F1 of A, right? If B is this side, what is f of B is nothing but F2 of B. And if on the common vertices both F1 and F2 have the same coloring, because F1 is an extension of C and F2 is an extension of C. Okay. So both F evaluates. So now all I have to show that F is a valid 3 coloring, right? So if you give me a valid 3 coloring of this portion, then I can get a valid 3 coloring for the whole graph. Now why this is, look at any edge. So either an edge, where are my edges? My edges are contained here, or edges are contained in the left hand graph, or the edges are contained inside the right hand graph, right? Because okay, now every edge is present in one of the graph, right? And so if this edge is present here, then F1 helps us. F2 is present here, then F2 helps us, because look at those endpoints. If F does not assign the correct color, then look at the map in F2, but that should also be violated because we are just following F2, but that doesn't happen, right? So given a 3 coloring for the left hand side and given a valid 3 coloring of the right hand side, we can get a valid 3 coloring for the whole graph. Okay. Now let's see what happens. So suppose EXC is 1. Okay. Now look at a coloring. Suppose this is 1. It means there exists a coloring F, okay, from let's say Vx to 1 to 3, which is valid coloring. Now, look at this coloring. I will say, let's call it Z. What is G1? Okay, look at a G1 coloring which is restricted to this side. Okay, so G1 is like G1 is, suppose this was like this is y and this is like y1, y2, right. So, graph G1 restricted to G1 is nothing but G restricted to Vy1, and what is G2? G restricted to Vy2. So, what is the property of G1? G1 matches with Vx, right, only left side. G2, what is the property G2? It matches with G2 in the right hand side. But then what does this show us? I have been able to show that there exists a coloring in Y1, right, which is a valid 3 coloring. It means definitely E Y1 comma G1, E Y1 comma C, okay, because of existence of G1 will evaluate to 1. Similarly, E Y2 comma C will evaluate to 1 because of existence of G2. So, this is how you will have to show that all the recurrences are correct. Okay. So, given a valid solution to here, I should be able to get a valid solution to my children. Given a valid solution to my children, I should be able to get a valid solution to my left hand side. Okay. Okay. So, this is how, so you should try to prove it formally, all these things and get. Okay. So, how many sub problems are we creating? We are creating 3 to the power w plus 1 times n sub problem, and each sub problem can be solved in constant time, assuming the children are solved. So, you can actually get an algorithm with running time O 3 to the power n. Okay. Okay. And that so the 3 coloring is FPT parameterized by Treewidth. Okay. So, what about more generally, given a tree decomposition of width w, you can do the same way C coloring in C to the power w, and basically this O star notation is used in parameterized complexity. To O star notation is used. So, when we write O star some f of k, okay, then this basically is a shorthand notation for f of k n to the power b. So, we actually do not explicitly write the polynomial dependence on the input, right. Okay. Okay. So, now given a tree decomposition of width w, vertex coloring can be solved in time w to the power w. It is a good exercise. Prove fact, and hint is so that the chromatic number of G is function of tree width of G, okay, and then you should be done. So, the other, let's say, so this is it. So, using this you should be able to prove it. But what is interesting is that this algorithm w to the power w is optimal. So, hoping that we can get an algorithm with w to the power little of w is unfortunately not possible, and hopefully we will have time to show such a reduction in the course. Okay. So, now we have seen 2 examples. In the morning we saw max independent set, okay. We saw example of max independent set in the morning, okay, weighted max independent set, okay. Now we saw 3 coloring. Now let us see another problem of our interest, that is dominating set, okay. Okay. So, what is a dominating set? You are given a graph G and K, you have to find set of K vertices so that every vertex of G is in S or has a neighbor in S. Okay. As before, Bx will denote vertices appearing in node X and Vx will denote vertices appearing the substituted at X. So, what could be the sub problems for dominating set at node X? Okay. 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 So let's make a first try. So whatever should be the first try. What is MXS? Okay, what is an MXS? Is like, okay, I'm looking at the node X and F is a subset of Vx. What we want to find a D subset of Vx so that every vertex in Vx is dominated by D and D intersection Bx is equal to S. So I decide which vertices from this bag is going to be the dominating set. I say, look, is there an extension, like what is a minimum size dominating set extending this, okay, S, and that dominates everything in Vx, okay. So let's see what is a problem with such a try, and okay, because notice what happens. As always I have told you, try to do divide and conquer. So if you do divide and conquer, then I have a separator and I have some vertices here and I have some vertices here. Now I have like this is like part A and part, like this is a portion. Now look at a vertex here, okay. Where are its neighbors? Its neighbors are here, here, or its neighbors are in my separator. So the only way we can get dominated is by this portion, right? So every vertex which is in A, so what information we can get? Every vertex in A must be dominated by vertices in A union S. Why? Because n of V is contained inside A union S, okay. And similarly for B. But now ask ourselves the following question: what about a vertex in here? Now this vertex, call it W, it could have a neighbor in A, some in S, and some maybe in B, right? So so for W in S, neighborhood of W is contained inside whole of Vg. Now, or rather say it could be in A, it could be in S, it could be in B, right? Okay, which implies that if I am solving recursively, right? Recursively, if I am trying to solve here, I may not need to dominate a vertex in S, right? Some vertices in S may be dominated from the B side. So basically we have to guess three set of information. Okay, which vertex in S is going to be in the dominating set? That's the first thing. And those vertices which are not going in the dominating set, are they being dominated from a vertex, or are they dominated from the B vertex, or they are dominated from a S vertex? So you have to decide. So basically if I would have been doing dynamic programming algorithm, then as I have been telling you the history, okay, so this is my bag and this is what it is. So we need to find succinct information, right? Succinct information or a table such that, okay, such that using this table and a future graph, we can solve DOM set problem for whole graph, right? So I do not see this portion, right? I do not see this portion, right? I do not see this portion up. So based on this information, I only see when I am doing bottom up dynamic programming, I do not see future. Based on locally, I say I don't know for any graph how this information look like, but I am going to have sufficient information from the below, so that you give me any graph from the top, okay, that graph could just look at the table. He does not need to lick the below graph, and with the help of this table and the graph itself, okay, this graph the top graph itself, it will be able to compute the minimum size dominating set of the whole graph. Okay. So now I said, look, irrespective of whichever graph it is going to intersect this S, irrespective of top graph. Look at an optimum solution of any of a graph, of my current graph, or that matter any other graph. Okay, it is going to intersect S. What are the possibilities? It could intersect. It could take some portion here. Okay, and for the remaining vertices, we have to decide, dominate from below, dominate from ever, future, whatever. Then once you have this, then you are basically looking for a dominating set for not the whole below thing, but you are looking for a dominating set of vertices which for all vertices, but for those which will be dominated in the future. Okay. So now we will try to make this intuition, this into a table. So that's our, okay. So as I explained to you, problem is that vertices in Vx can be dominated by vertices outside Vx. So this leads to the following sub problem. So we have at this node we partition x S1 S2, okay, okay. So the size of smallest set from below, so that every vertex in Vx minus Bx is dominated by D. So every vertex here is definitely dominated by D. D intersection Bx is equal to S, and D dominates every vertex of S2. Okay. Okay. So you get my point. So we have two things, S1 and S2, okay. And what is it like? So as I told you, right, some vertices here could just be dominated by these green vertices, right. So dominated from below, which also means that they are probably dominated from here, okay. So this is what we are trying to write here. It's a size of the smallest set contained from below, which has some property. Every vertex from here is dominated by D. That's one thing. D intersection, you are going to pick S1, okay, from here, and D dominates every vertex of S2. So how many such problems are you going to create? And the vertices which, okay, so what is this? You are going to be, so for every vertex, what are the three states? For every vertex, the states are in dominating set, okay, okay, in dominating set, that is D intersection Bx is S, okay. Okay, right, dominating set, okay. Now, so those are automatically, okay, vertices in Bx minus S1, which is like vertices that are dominated from below. So they are not part of the dominating set, but they are dominated from vertices in the Vx. So in particular, they are dominated by D. And what we have not care about dominating, the vertices in Bx minus S1 union S2 are those vertices in this picture, right, which will be dominated from future, okay. So there are some vertices which will be dominated from outside. So you are basically in some sense you are trying to find a dominating set. So if I have to write in other alternatively, what are we trying to do here? We are trying to find dominating set of Vx minus, I would say, S3, which is nothing but, right? So, you are dominating everything but this, and whose intersection with B of x, bag of x is S1, right? So, look at the vertices in the bag. Some of them goes to this dominating set, some they do not go to the dominating set, that's fine. But among those, I decide which one of them are dominated from below and which of them will be dominated in future or will be dominated by vertices which is not present in Vx, right? So, once you made decision, then you are perfectly fine. Okay. Now, so the question is, how can we solve sub-problems Mx, S1, S2 when X is a joint node? Rest of them are very similar. Okay. So, what do you know? Each vertex of S2 is dominated from the left child. Okay. Right. So, look at joint node, right? Here it is, right? So, remember in joint node, what is your goal? Now, you have X, S1, S2, and the some people you do not care. But now, you have to decide what is the property. S1 is a set of vertices which is going to be the dominating set. Now, you decide for S2, right? S2, okay, I don't know about S2. So, I want to fill, let's try to fill okay. Let's try to fill M, X, S1, S2. Okay. I have to decide, okay, right? A vertex in S2, look, remember what is our criteria? A vertex in S2 needs to be dominated from somewhere, right? Right? Because we are looking for a solution for the whole graph. So, if you look at a graph perspective, look at this graph perspective. So, the way we make is this, here it is, okay. Okay, even better, let's draw like this and this, okay. Okay. So, now this is my bag, okay. Okay, this is my node X, okay. This is my portion of S1, this is my portion of S2, and we do not care about this. So, basically it is a S1, you are in the dominating set, you are dominating from the left, S3 is something which I do not care. I do not care whether to dominate. Now, look at S2. Now, I do not know from, so S2, so if I have to fill S2, okay, right. So, I ask myself, look, M, suppose this is a child Y1, Y2. So, M Y1, okay, and so what is this going to be? Minimum of, okay, M Y1 S1, okay. Now, I decide for S3, right, for S3, maybe some of these vertices should be dominated from the left side, some of these vertices may be dominated from the right side. So, now what I will do, M Y1 S1, S2 say left plus M Y2 S1 S2 right, or maybe both, I do not care. I mean, maybe you are dominated from both, but right. So, basically you have to go through all such possibilities and take minimum. So, basically how many such sub problems will you generate? You will generate as many sub problem as many as partition of like division of S3, and that is why you will generate like S2, maybe you can dominate it from the left or you dominate it from the right or dominate it from both, right. So, that will tell you 3 partition of S2, and that 3 partition, like from the both, then you, so if you decide for S2 left, right, both, okay, then what will be the S2 left is like L union both. What is our S2 right is right union both, right. So, you put this in, right. Now, you say you compute these values, okay. For each of these values you compute the number, right, and then you have to subtract the S1 value, cardinality of S1, because that is common to both, and among all such possible values you will take the one which minimizes. So, now notice, to fill this table how much time will we take? We will take, to fill each of this table, we will take 3 to the power mod S2 time, right. So, in worst case this could lead to 9W, like 9 to the power W n time algorithm to do this, and trust me, like introduce node, forget node are much more easier than this, okay. And so, this implies that if you do this, okay, it could lead to, you know, 9 to the power W kind of algorithm, okay. There are ways to improve all this, but like I will not tell you all this. I mean, you can get down to some 5 power W, 4 to the power W, like by some clever simple tricks with who is dominated from which side or not, but let us not worry about those things. In fact, we can get down as good as 3 to the power W, right. So, like this join node looks like that we create to fill one entry, we are creating lots of sub problems, which is true in some sense, but we can do some very clever way of filling these tables, and actually we can get the running time of the algorithm for dominating set parameterized by Treewidth to just 3 to the power W, which is cannot be beaten, in the sense that we will be able to show later that that you do not have, say for example, 2.9 to the power W time algorithm for dominating set, for example, of course under some conjecture, okay, not possible, okay. So, but I just wanted to give you the feeling of, you know, like you have to have a feeling of notion of how partial solutions look like, what is the notion of left, right, and all possible partial solutions basically creates an entry in the each possible partial solution correspond to a entry in the table, and the way we make a table is that given any right hand side graph or the given any future graph and this table, it can compute the solution of whole object just by looking at this table and looking at the right hand side, okay. So, okay. So, the last example that I want to talk about is Hamiltonian cycle, okay, which is slightly, okay. So, let us try as a thought process. I have always told you that like, okay. So, let's look at Hamiltonian cycle. So, what is Hamiltonian cycle? Is basically a cycle on which every vertex appears, right. So, a cycle is called Hamiltonian if every vertex is present on this, and the question is whether given a graph G, does there exist a Hamiltonian cycle? Okay. Let us do our thought process again, okay. Again our thought process is our separator, left side, right side, okay. Now, what is the notion of, what is the meaning of partial solution? Partial solution basically means how will if I look at any solution and if I look at the intersection here, how will it behave? How will it look like? Now, look at any Hamiltonian cycle. How could a Hamiltonian cycle look like? A Hamiltonian cycle, suppose, look, it touches every vertex. Maybe it comes like this, like this, like this, passes, okay, maybe, okay. I don't want to draw such nice picture. It could be just like this, right? Okay. Or maybe just to make our life a little bit easier, let me try. Okay. Okay. This is slightly more nicer to have a look. Okay. Now notice, if I look from the left hand side perspective, what do I see? I will see something going, okay, and again going after this. Okay. Now notice that once you have drawn this, okay, right. So this is what we see. So what is the property? The property is that some vertices, look at every vertex. So we ask ourselves, if I look at the left hand side, what are we looking for? What is my partial solution? So partial solution is basically some set of paths. And what is the property of these paths? These paths somehow start in the root, like in the separator bag, and end in separator bag in some sense. And so what is the property? That these vertices, if I look from the left side, they are getting one edge on this Hamiltonian cycle from the left side. Okay, so its degree is 1. But some vertices, for example, here, look at this, it's in the separator side. But what is its degree? It's 2 because it's here. Maybe there is some vertices here whose degree will be 0 because maybe they are getting, like the cycle is coming in some way and they are going completely. So, so we are looking for an Hamiltonian cycle, but will have some property. What we will specify you. Look, these are 2 degree 1 vertices. It means you give me a cycle from below, cycle which like a set of disjoint paths with a property which spans every vertex from here if its degree is non-zero, and it has this property that it starts from here, it ends here. So I will also tell you the set of paths, what are its end points in the sense, like I will tell you, okay, it starts at this, it is, so it's like I will give you pairs, right? And I will tell, look, I will tell you how can I define these things. I say, hey, look at these pairs. So for example, here AB is one pair, CD is maybe another pair or something, okay, or maybe D is another pair, and for these things we will have some other specification, okay, and we'll say, hey, is there just a set of disjoint paths joining A to B, C to D, and maybe D to E or whatever, maybe we call it this, and for the vertices on the bag which is a 0, I will not care. So I am looking for these disjoint paths that covers every vertex in the left side and has this property, right? So this is how a partial solution will look like, and given this, like any partial solution can be described. So it could be it can be described by defining some set of pairs, defining some degree 0 vertices, degree 1 vertices, and so on and so forth, and trying to find a set of disjoint paths satisfying these specified properties. Okay, so this is what is being done when we try to do this. Okay, so if you look at this, now we are looking from this perspective of vertices appearing in node X. Vx is vertices appearing in the subtree rooted at X. And if H is a Hamiltonian cycle, then the subgraph HVX is a set of paths with endpoints in the bag containing this, right? So now notice what is Bx0? These are those, like when I look from this, when I look at only edges which is contained inside this, then the edges here are not there. So from the down perspective, these vertices are of degree 0, right? So from the outside world, because the Hamiltonian cycle is going to pick up like this. Okay, so those are degree 0 vertices from. Now, what is the property of degree 1 vertices here? Right, degree 1 vertices is basically these are like paired. So from the it goes and the cycle leaves this and completely crosses immediately to the other side. So you will have these vertices will have degree 1, okay. So these will form a pairing, right? This will form a pairing. So what are the vertices of degree 1? Are those vertices which uses one edge this side and one edge on the top. So, and some of these vertices here are degree 2. Basically, I mean, they are degree 2 in the sense it means that they're both the endpoints are in the left, are in the below side. So this is what we are trying to look for. So the subsets Bx0, Bx1 of B have degree 0 and 1, 2 respectively, and we have a very specified thing that there is a matching on Bx1 vertex. So degree 1 vertices should be matching because I am coming in from one and I am leaving from the other. Similarly, so this is the pairs which you will get. So for example, here A and B, and maybe maybe I didn't draw it properly, otherwise C and D would have been the corresponding pair. Okay. Okay. So how many such subproblems are there? So basically, first you partition them into degree 0, 1 and 2. So that's like 3 to the power W. And now for the degree 1 vertices, you have to find the pair. So basically it's a partition of some subset of vertices into pairs. So like, right, and that is upper bounded by W to the power W such pairs, right. So you are specified by 3 set of information, which vertices have degree 0, which vertices have degree 1, which vertices have degree 2, and what is the pairs of, what is the pairing in the vertices of degree 1. Okay. So for each subproblem, we have to determine if there is a set of paths with this pattern, right. Okay. How we will do this for different types of nodes, assuming that all the subproblems are solved for its children. So again, we will see what can we do in introduced node, what can we do in forget node, so on and so forth. So no children, Bx equal to 1, trivial, it's a single vertex, so you can fill up everything. Now look at a forget node. This is slightly easier. So what is happening? So if you are forgetting for some vertex V, okay, then what is the point? If I am forgetting a vertex V at this point of time, which basically means that after this, all the, like V does not have any more neighbor outside. So V has all the neighbors inside, which implies that if I am looking for some characteristic vector here, then I should put V equal to be put partition V into degree 2 and check, hey, like, so the subproblem it will be like, okay, fine, V is missing, like this is a forget node, I just put V in degree 2, right, that's it, and with the same pattern. So this will exist if and only if this. So for a node below, we have already computed and we check if this is 1 or not. If this is 1, we put it 1 here. That's it. Okay. So we put V in the degree 2 and ask, right, the subproblem is equal to the subproblem same degree 0, same degree 1, but now we are forgetting this V vertex. It means the Hamiltonian cycle will contain both the edges incident to this V here itself. In other words, I will say, hey, is there a disjoint path with this pattern where V has degree 2, which we have already stored in the below. So based on its answer, we will put 0 or 1. Okay. So we are asking, is there a pattern, and if there is a pattern of this nature, then we say 1 or we put 0. Okay. So now let's look at the introduced node. So introduced node will have several cases. Okay. Either the easy case is that B belongs to V has degree 0, then it is equivalent to that. I mean, if V has degree 0, then you are looking for a pattern without this vertex, because that vertex is not appear, this vertex V does not appear on the path system that we are looking from the below. So you put minus V0, B1x, B2 for node Y, right, and that's it. So if you forget this and you look at this, if this is 1, then you put 1, otherwise you put 0. Okay, right. So if we have such a subproblem for node Y, then you put, then you are happy, otherwise you are not. Okay, right, because if you had such a solution, that implies like you just take the same disjoint solution here, like same pattern solution, the same pattern here, that will also correspond to a pattern solution when V has been assigned 0. So a solution here corresponds to a solution here. Okay. Case 2. Now, if V is in Bx1, what is the property of this? We know that every neighbor of V in Vx is in Bx, because this is the time when a vertex is introduced, then all its neighbors at that point is in this bag. Thus, B has to be at least adjacent with one other vertex of, right, like of Bx, right? You get my point? The point is that, look, what is, now if I am going to ask, oh, V has degree 1, if V has degree 1, which implies that one of the vertex, its neighbor has to be adjacent with one other vertex of V. So, let us ask, is there a sub problem by0, by1, b2i, m prime of node y, so that making a vertex of by adjacent to V makes it a solution for a sub problem bx0, bx1, b2x, m of node x? You just ask yourself. Then for different choices, right, now, right, so this will correspond to, look, this is degree 1. So, the only possibility is that his other neighbor, look, I mean, it could just be an edge here, that is also fine. Okay. So, but this V could, so you are making a pattern here. So, either this vertex will get its neighbor in this from B to X, then which could look like this, or, right, right, or I mean, or you could have a pattern like this and this, and it is getting one from here. You could also be that, you know, it could be just like this. So, then it is just like the pattern itself is this. Okay. Okay. So, yeah, so several cases will appear, and you have to handle each of them cases by looking at what subproblem to make, what subproblem not to make, and so you do it case by case for everything, and you deal with. I am not going to details. Have a look at these. I mean, these slides are properly done. It should help you. Okay. So the bad case was when this was degree 1, and if V is in B1x, but what is the property that if V is in B1x, right, and then similar to case 2, but now two vertices of By are adjacent with V, okay, and again you deal with them and like deal, okay. So, yeah, so there will be several cases when you introduce comes, and you have to deal with each of these cases, but like I will omit this. You can have a, I will provide these slides, you could have a look at it. Okay. And similarly, okay, if you have two children y1 y2 with bx by bu2, and then a solution H is a union of subgraph this and a solution this. So, you have to check whether their union is a solution at node x. So, for any two subproblems y1 y2, we check if they have a solution and if their union is a solution for this node x or not, okay. And yeah, so basically H1 will provide you some sort of connectivity, H2 will provide you some sort of connectivity, and you see, can you achieve this part of the solution using all these things. If you are able to succeed, then you are happy. If not, then yeah. So, TAs will probably also spend some time doing on this, but all I want to tell you that you could do all kinds of problems doing a simple dynamic programming algorithm, okay. And if you do this the way we have done, is like you will get w to the power w kind of algorithm here, but after a lot of hard work it is possible to get some c power w algorithm, right, but that requires different techniques and different methods, and that we will not talk about in this course, okay. So, I hope I have given you some idea and some way to do dynamic programming algorithm over graphs of bounded Treewidth, and I hope you can make use of it, okay. Thank you.